Hello, welcome to the last press conference of today on Dawn's closest look at Vesta. And we have three people speaking. Maria Cristina De Santis is the Dawn mission co-investigator and the leader of the visible and infrared spectrometer and works at the National Institute for Astrophysics in Italy. Harald Jessinger is the Dawn mission participating scientist and works at the University of Münster in Germany. And Carol Raymond is the Dawn Deputy Principal Investigator, and she works at the Jet Propulsion Lab in California. Christina.
Carol, yeah, thank you, Barbara. I'll start off with just a couple of remarks. First of all, I wouldn't call it work because it's just a lot of fun what we do, and we're really happy to share that with you today. Since arriving at Vesta, which is Dawn's first target, back in July, we've been slowly getting closer to the body as we proceed through our different orbits. And right now we're in our closest orbit, the lowest altitude, where we're skimming over the surface at just over 200 kilometers. So we've been seeing a lot of very detailed views of the surface and able to make some very precise measurements. So we're happy to be here to share those with you today. And I think you'll agree that Vesta is quite a beautiful and intriguing body. With that, I'll turn it over to Harry.
Okay, good afternoon. So on behalf of the entire framing camera team, it's my pleasure to report to you some of the latest results of our investigation with the camera. In this slide, you see a map projected mosaic of images of Vesta, with the equator basically running horizontally through this image. South Pole is here at the bottom, North Pole is here on top. And you can basically take away three things from this particular image. First of all, we were able to cover over the last few months Vesta with a large number of images with increasingly higher resolution, up to 20 meter per pixel. Second, because there are only a few shades of gray in this image, you might get the impression that Vesta is actually a more or less homogeneous body, but I will actually show you that this is not the case, and that Vesta is actually characterized by tremendous color differences. And third, as you can see, at the North Pole, we have still missing data. The areas there have been in shadow since we've arrived at Vesta, but will be increasingly be illuminated over the next few months, and we will basically cover this gap up there until we leave Vesta. Next, please. So here you see two impact craters. In the Aquilia crater, which is the one at the bottom, and an unnamed crater to the northwest of it. So all the images that I'm going to show you today are from the Dawn high altitude mapping orbit from about 680 kilometers above the surface, which lasted from September 29th to November 2nd of 2011. This particular image shows a sort of a ridge and groove terrain over here, and the two craters have very sharp crater rims, indicating that they are probably relatively young. And in particular, the useness of this crater, of this particular one, is also documented by these blocks that you can see at the floor of this crater, and in general the very sharp morphology. And in addition to this, you only see a few impact craters that are superposed on the ejecta blanket. That would be the ejected material of this crater. So that all indicates that this is a relatively young crater. Next, please. Here you see an RGB color composite where we use the brightness at the 750 and the 440 nanometer channel, which is displayed in this particular image as red. We have 750 over 920 nanometer displayed as green, and the 440 over 750 displayed here as blue. So this particular composite image was done to sort of enhance subtle color differences, and what you see here in these green colors, where's my mouse here? Over here, for example, this shows you the strength of the 1 micron absorption band. This is a very characteristic absorption band that allows us to distinguish between different types of pyroxenes on the surface. Pyroxene is a mineral that's very common in volcanic rocks here on Earth too. The reddish colors are also indicating differences with respect to the green colors, might also be an effect of different weathering processes, and space weathering is basically a measure of how long this surface has been exposed to the micrometeorite bombardment and also the cosmic rays. So this particular crater here shows a very dark blue prominent ejecta blanket, and right now we interpret this as material that was excavated by this crater from deeper layers within the crust. Next, please. So here we have a combination of those two images, the monochrome image that I showed you first and the RGB composite that I showed you last, and we are now basically simultaneously looking at the morphology and the color information, and as a result we can see that, for example, relatively small impact craters that are close by have very distinct and different color properties, so indicating that the composition of the material on the surface or in the subsurface varies very quickly, even at small scales. You also can see this sort of purple colored area here, which is in a morphologic depression within this more bluish, within this more greenish area. So we get a lot of detailed information, and these particular images help us tremendously in mapping the differences on Vesta. Next, please. So here we have another monochrome image. This time it's of crater Vividia. The impact occurred at the edge of a cratered highland terrain and appears to be located in a gentle depression like this, so presumably an old impact crater. This particular crater is, has a very strong ray pattern of ejected material, and on the Moon, for example, such ray patterns are indicative of either compositional differences or, again, differences in the maturity, so how long this particular crater has been exposed to micrometeorites and cosmic rays. Next, please. The Vividia crater exhibits a particularly colorful ejecta blanket and interior, which demonstrate that the surface and subsurface of Vesta are highly heterogeneous, and this might reflect some complex interplay of ancient volcanic deposits or processes and impact processes that basically shaped Vesta's crust. Next, please. So again, here's a combination of the RGB image with the monochrome image showing the complex connection between morphology and color information. And to finally wrap up, next please, I would like to introduce you to the framing camera that actually took all these fantastic images. The framing camera, which is displayed on the left side, is a joint development of two German institutions, the Max Planck Institute of Solar System Research and the DLR Institute of Planetary Research. There are actually two cameras, two identical and redundant cameras on board of the spacecraft that can be operated independently. So this would enable us to continue operations even in the case that one camera should fail. In the right image, you see the Dawn spacecraft with the folded solar panels and the large high-gain antenna to communicate with Earth. And the two cameras are actually located up here. Okay. So to sum up, we are really happy about the performance of the camera, and we are very excited to see Vesta close up. We have been waiting for a very long time, for decades, some people, to get these images. And what we see right now is literally just the tip of the iceberg. Okay, we're just starting getting really, really good information back of Vesta, and we're going to understand Vesta in much greater detail once we start really working on all these fantastic data. And with that, I would like to hand over the microphone to Maria Cristina De Sanctis, who will present to you some of the really spectacular images, or spectra actually, of the VIR instrument.
Thank you, Aaron. Next, please. So, the VIR results from Dawn suggest that Vesta surface is continually reworked, and based on the high-resolution hyperspectral images, we think that some places on Vesta are more recently relatively young, while some others are relatively old. And the increasing resolution obtained in the last months help us in defining the details of the Vesta surface and mineralogy. VIR is an imaging spectrometer that provides images in more than 800 different wavelengths, from the UV to the infrared, 5 microns. And for this reason, it also provides spectra in the visible and the infrared wavelengths, giving insight on the material composition. So, coming near Vesta, Vir was able to acquire images and data from the same zone with an increasing resolution, from about 700 meter per pixel during survey up to 70 meter per pixel in AMO, and was able to distinguish details that were not visible on the surface in the previous months. Here we focus on Tarpeia crater, that is the small box, red box, encircled in the red box, and is located near the south pole of Vesta. And Tarpeia was observed during all the different orbits of Dawn, so from survey to LAMO. And next, please. So in the next images, in the next slide, I will show you the Tarpeia location during these different orbits. This image was taken during survey in August 11, and was taken with the resolution of 700 meters. And next, please. As Dawn comes nearer to the asteroids, more details are visible, and this is an image taken during HAMO with the resolution of about 200 meters per pixel. So you can see how the increasing resolution helps us in distinguish different details. And next, please. Finally, we see the LAMO images of Tarpeia acquired with a pixel resolution of about 70 meters per pixel. And next, please. The LAMO data were elaborated in false color to show details of the Tarpeia crater. So you see that in these false color images, you see different materials that came out from Tarpeia. Next. And a more detailed image of this Tarpeia crater has been elaborated to obtain these other false color images, and the colors correspond to different spectra. So you see that studying the spectra corresponding to different areas, the Vir team and Dawn team was able to make a first classification of this material outside and inside the crater. The spectra tell us how different is the material, and we can recognize in this case 3 different classes: the yellow, the blue, and the brown. And the brown and yellow material have similar composition, but they are seen under different illumination conditions. So the spectra looks like different, but the spectral characteristics are similar. The spectral parameters are similar, and these materials are more or less the same. While the blue class is a different material. Next, please. The blue class on the edge of the rim is interpreted as a different material with a spectrum that is typical of the fresh material. And this material must be been exposed during a landslide on the crater walls or a similar, more recent event on the crater side. So we are particularly interested in this blue material because it is a less altered material. So it therefore is more similar to the original material of the asteroid Vesta. Yellow and brown material can be considered as older material with less pyroxene. The signature of the pyroxene, that is this common mineral on Vesta surface, is less prominent, while in the blue, youngest and freshest material, the pyroxene is much more intense. Next, please. The infrared part of the spectra also give information about the temperature of the surface, and the spectrometers has also gotten the highest resolution surface temperature maps of any asteroid visited so far. And in this false color image, we see the emission at 5 microns that give us information about the temperature of this area. The zones that appear brighter are at higher temperature than the darker zone that looks like in shadows. And in this particular case, the temperature in these Tarpeia areas go from about minus 100 Celsius in the darker areas and up to about minus 23 Celsius in the bright crater floor of Tarpeia. So to conclude, the VIR data giving us detailed images and spectra are particularly important in understanding the processes that act on Vesta. And in particular, we see that Vesta's skeins is constantly getting a sort of facelift, and there are portions of the surface of this old body that are relatively young. And next to Carol.
Thank you. Okay, I'm going to switch the gears a little bit and talk to you now about Vesta's gravity, which is a property of the entire asteroid. And so I'll just take a moment to explain how we're measuring that. We're doing this the way many planetary spacecraft do by making very precise measurements of the Doppler shift of the radio signal when that large high-gain antenna is pointed at the Earth. Which we do several times a week in the low-altitude orbit to return our data. So during those telemetry sessions, we measure the precise accelerations of the spacecraft, and from those, we can deduce the gravity field. So if the spacecraft is flying over a mountain on Vesta, then that mountain is pulling the spacecraft towards it as it's approaching, and then it speeds up as it goes over, and then it slows down again. So we can measure those changes in velocity accurately enough to be able to resolve the gravity field. So I'm going to show you now an animation of Vesta with the body's shape on the left in a shaded topographic globe, and then the gravity field on the right expressed as a color contoured field. The heights relative to a reference ellipsoid of the shape go from about minus 22 to 19 kilometers. And the gravitational acceleration, which is shown on the right, varies from about minus 1,200 milligals up to 2,000. Milligal being a centimeter per second squared. What is very obvious when you compare these two renderings is that most of the gravitational acceleration is due to the shape of Vesta. So, for instance, the red high topography that's coming into view is high gravity anomalies associated with this high topography that you can see as the body rotates at the equator. The central peak of the Rhea Silvia Basin at the southern hemisphere is also showing up as a positive. Many of the impact basins show up as negatives. So essentially, when material is closer to the spacecraft, it's showing up as a gravitational high, and when material is relatively farther from the spacecraft, being in a deep basin, then it shows up as a gravitational low. So in order to understand better what the crust of Vesta looks like, or what the gravity can tell us about the crust itself, we strip off the gravity signal from the topography. So we essentially level the topography. All of the basins go away, all the mountains go away, because we've corrected for them using an average crustal density. And when we do that, what's left over are anomalies which range over a couple hundred milligals in range. And that is due to the deviations of those areas from this average crustal density. So where we have the warmer colors in the right side, those are indicating areas where the crust is relatively denser than the average model crustal density that we used. And by the same token, the blues are showing you lows. So when we compare those corrected gravity anomalies to the topography, which is shown on the left, looking at the southern hemisphere as a whole, and where we're showing the outlines of the Rhea Silvia Basin and the underlying Venenia Basin, we see that the central peak of the Rea Silvia Basin, which is the red area just to the left of the center, here is associated with a positive corrected gravity anomaly, which we can infer is telling us that this crust is relatively denser. So this would be consistent with this crust being uplifted from a deeper layer of Vesta where the crust is more compacted and the mineralogy is different, and the expectation is the crust would be denser. We also see that the outline here of the rim of the basin shows up as a relative a low gravity anomaly. And that would be telling us then that we've subtracted too much using our average crustal density from the gravity signal, and therefore that this rim is likely less dense, consistent with it being more brecciated, porous type of material that got thrown out during the impact. So we take away from this a couple of things. One is that, like most solid rocky bodies of the solar system, the shape of the body dominates its gravity field at almost all wavelengths, but that taking that into account, we are seeing some significant variations in the corrected gravity that are giving us some information about the crust of Vesta itself. And I just wanted to end with a couple of comments about where the mission is going over the next few months. This is just an animation showing you the spacecraft flying over the surface of Vesta and reinforcing the fact that right now we are at a very low orbit. We will be leaving this low altitude orbit on May 1st, and we will begin to spiral out to the altitude at which we made our mapping at the high altitude on the way in. We will take another series of images and spectra at that altitude to fill in the dark northern tier that Harry pointed out at the beginning. And then we will continue to spiral out, making several more observations of the rotation of Vesta until the point where we escape on about August 26th. And then we will be on our way to our second target, the protoplanet, dwarf planet Ceres, which we will arrive at on February 1st of 2015.
Really excellent images you show there. I already had one request, so if you'd like to send me your PowerPoint presentations, I'd be happy to upload them to our media website. Okay. Let's open the floor for questions.
Hi there, Jonathan Amos, BBC. How much of the unseen northern hemisphere will you see before you leave? I mean, will you see it all? And what are you expecting to see? Are you expecting to see any features related to the giant impact crater in the south reflected in the north in some surface features of some kind?
We expect to be able to map to within 5 degrees or so of the pole. And as I said, as we leave Vesta, we keep looking back, and when we get far enough away, we're watching Vesta rotate under the spacecraft like we did on the way in. So we will see all the way to the northern pole. The question is, at what resolution? But we expect to have data at the equivalent resolution to our initial high-altitude mapping orbit up to 85 or so degrees. And then the rest will be at lower and lower resolution. The sun will only cross the equator on August 20th, and we escape on August 26th. So by that time, we're already fairly far away. We are expecting to see some of the oldest crust on Vesta in the north, because the Rea Silvia impact had such a a huge resurfacing effect that some of the crust that we now are interpreting as being some of the oldest is right at the limit of what we're seeing. So we do expect to see more of that, and are interested to see if predictions of antipodal features to the giant impact basin may exist there as well.
Any other questions? Any questions from the web stream, Julia?
Sorry. And do your gravity measurements tell you anything about internal, in terms of differentiation, how far this body may have got, in sorting out its internal layers, a core?
They do, and we plan to be talking about that very soon.
When?
In a few weeks.
Any other questions? We have to wait a few weeks for more questions. Okay, if there are no more questions, let's end here. Thank you all very much for coming. Thank you for your excellent presentations. I have two announcements to make. There's an exhibition, a photographic exhibition going on downstairs on the Japan tsunami, so photographies of before and after. And the photographer Stephen Vaughan is giving a talk now at 5:30 in room 11, also downstairs, near the exhibition. And as for a press conference, we restart again tomorrow, earlier than usual at 9, with a press conference on space weather effects and forecasting. Thank you. Bye.